Okay, so this is our second day of related rates. Are there any problems from the homework that you want to see done? You just couldn't get to come out for whatever reason. Number 7, okay. All right, let's work through that one. Okay, so the top of a silo has the shape of a hemisphere. It's a diameter 20 feet. It's coated uniformly with a layer of ice, and the thickness of that ice is decreasing at a rate of 1/4 inch per hour. So how fast is the volume of ice changing when the ice is 2 inches thick? So I like to first draw a picture. So we've got a silo, which is just a half a sphere. And this silo is 20 feet diameter. So I'm going to put a 10 for the radius. All right, and then it's coated uniformly with a layer of ice. So like this layer of ice on top of the hemisphere. And that ice is melting, decreasing at a rate of 1/4 inch per hour. How fast is the volume of ice changing when the ice is 2 inches thick? All right, so the thickness of this ice is changing. It's a variable, right? So we could call it x. And let's see, I did this in feet, and they're giving me my rate in inches. My two rates are in inches, so maybe this 10, I might write that as a 120 inches instead of 10 feet. All right, so let's see, what am I given and what do I want? So the rate I'm given is the thickness of the ice at the rate at which that thickness is decreasing. So how would I represent that using the variables I've put in my picture? Dx dt. And because x is decreasing, the thickness of the ice is decreasing, dx dt should be negative. So this is negative 0.25 inches per hour. And we want how fast the volume of ice is changing. So I want the rate of change of the volume of the ice. So we'll call that dv dt, letting v be the volume of the ice. Okay, so how fast is the volume changing when x is 2, right? When the thickness of the ice is 2 inches. All right, so I have to come up with some equation that relates v and x. V is the volume of the ice, not the volume inside the silo, but just of the ice. Okay, so volume of the ice. Well, that would be the total outer volume minus the volume inside the silo. So the volume of a sphere, what is that? 4/3 pi r cubed? Yeah. Okay, so this is going to be 4/3 pi, and then the radius is going to be 120 plus x. So that's my outer volume, silo, and ice. 4/3. Oh yeah, because it's only half. Yeah, good call. Yep, it's only half a sphere, so when you multiply 4/3 by half, you get 2/3. Okay, so that's 2/3 pi r cubed. Then I have to subtract the volume inside the silo, which is going to be 2/3 times pi times 120 cubed. All right, so now I have a volume that's relating, an equation that's relating volume and x, v and x. So that's good. The next step is typically to take ddt of both sides. But I think I'm going to try to simplify things as much as I can before I do that. Just to make taking the derivatives easier. So volume 120 plus x, that's really not worth multiplying out. I'm going to leave that as it is. So this will be 2/3 pi times 120 plus x cubed. But 120 cubed, that whole thing is just a number. So I guess if I'm going to take d dt of it, it's just going to go away, right? So why bother simplifying it? Okay, sorry. Just wrote down the exact same line twice. Okay, so now I introduce d dt to both sides because I have an equation that relates x and v, but the thing that I know and the thing that I want are dx dt and dv dt. They're rates of change, and this equation has no rates of change in it. So to introduce some rates of change, we take the time derivative of both sides. Okay, so d dt of v is just dv dt. All right, and then d dt of 2/3 pi times 120 plus x cubed. Well, I'm going to take the derivative as though my independent variable were x, right? As though this said d dx, and then I just have to multiply by dx dt. So I'm going to use the power rule here. I bring the 3 down, and it's going to cancel, and I'm going to get 2 pi times 120 plus x squared. So that's my power rule on my stuff, but then I have to multiply by the derivative of the stuff. The derivative of 120 plus x is, oops, should be times, dx dt. Right, the derivative of 120 is 0, and the derivative of x is dx dt. And then d dt of this constant is just going to be 0, so that goes away. All right, so now I plug in the stuff that I know at the snapshot in time that I'm interested in, which is when x is 2. I want to know dv dt when x is 2. dx dt is constant, so I replace dx dt with a negative 0.25 and my x with a 2. Oops, forgot to put in the 2. Okay, so let's see. 122 squared times 2 times negative 0.25 is negative 7,442 pi. Or if I want to get a decimal, negative 23,379.7. And this is a rate of change of volume. So its units are cubic inches per, what was it, minute? Hour? Hour. You just go back up and look and say, oh, the other rate they gave me was in hours, so the rate that I end up with comes out in hours. All right, is that the answer? Maybe they changed it to cubic feet? Oh, okay. All right, good. Where'd you make a mistake?
I was using diameter instead of radius.
Ah.
2 places, so I couldn't figure out
Uh-huh.
where it was.
Anything else from the homework that you want to see? All right, well, let's work through a couple that I had prepared for you. If a, excuse me. If a snowball melts so that its surface area is decreasing at a rate of 1 square centimeter per minute, find the rate at which the diameter decreases when the diameter is 10. All right, so we've got a snowball. Just mark the radius. All right, what's the surface area of a sphere? Well, I suppose before I do that, I should do what I always do. What do I know? What do I want? Right. Okay, so what rate am I given? The derivative of surface area. So we'll call that ds dt. We'll let S be surface area. So ds dt is -1. Because it's decreasing, so the derivative should be negative. And I want the rate at which the diameter decreases. All right, so I want dd dt, right? We'll use capital D for diameter. When d is 10, or r is 5. Okay, who knows the surface area formula for a sphere? Is it? I don't know. We'll look it up. Okay, so surface area is 4 pi radius squared. But instead of putting in radius, I'm putting in diameter over 2 because diameter is the variable that they asked me about. So I could rewrite this as surface area is, this would be d squared over 4. So my 4's would cancel, and I just get pi d squared. Not taking a derivative, just simplifying. I just took that fraction d over 2, square the top, square the bottom, and the 4's cancel. All right, so I now have a relationship between the two variables of interest, surface area and diameter. So now I introduce some rates of change by taking d dt of both sides. So ds dt is going to equal d dt of pi d squared. So the derivative of pi d squared would be what? 2 pi d, not quite done, times d dt, chain rule. Because diameter is a function of time, so that's really like an inside function, that capital D. Okay, so now I can plug in the stuff that I know for my snapshot. I know that ds dt is -1, it's constant, and I'd like to know d dt, so I'm going to be solving for that when d is 10. So I plug in a 10 for d. So I have -1 equal to 2 pi times 10 times dd dt. And we get dd dt is -1 over 20 pi. -0.016. What are my units on dd dt? What's d represent? D represent a diameter. How do you measure? What are the units on a diameter? Just centimeters. So this is centimeters per minute. Any questions on that one? These are kind of fun, right? No reaction. Okay. All right, so I'm going to let you guys start this one. I want you to draw the picture and write what I know, what I want. All right, let's draw the picture. Spotlight on the ground, aim towards a wall. So here's my light. Here's my wall. The light is 12 meters from the wall. A person that is 2 meters tall walks from the spotlight towards the wall. Okay, so here's my person. And they're walking that way towards the wall. Find the rate at which the person's shadow on the wall is changing when the person is 10 meters from the wall. All right, so I kind of drew that too perfect. All right, so there's the line of a ray of light, right, as it hits the person, and this would be the length of their shadow. Okay. So this person is 2 meters tall, and we want to know when some rate of change when the person is 10 meters from the wall. So let's call this distance, the distance from the wall, x. That way it'll be easy to plug in. At some point, we'll just replace the x with a 10. All right, so if that distance is x, what is this distance from the light to the person? -12 minus x. All right, and then this will be this is the height of the shadow where this beam of light hits the wall. So we can call that y. Assuming that the wall is built perpendicular to the floor. So we have a right triangle. All right, so that's good. We have a picture. We've got some variables in it. Let's see, what do I know? And what do I want? All right, I know that the person is walking towards the wall at 1.6 meters per second. So that's going to be dx dt. The rate of change of x is the speed of this person. Now, is this distance x increasing or decreasing? Decreasing. As this person walks towards the wall, x is going to get smaller, which means that dx dt should be negative. All right, and then I want the rate of change of the person's shadow, right? The rate at which the person's shadow is changing. Okay, so that would be y, is the length of the shadow. So the rate at which it's changing is dy dt. When x is 10. All right. So can I make some equation to relate x and y in this picture? Yeah, these are two similar triangles, so I can set up a proportion based on the side lengths. So I've got a small triangle here and a larger triangle that is similar in blue there. So I can use the proportionality of similar triangles to write an equation. So let's see, in my little triangle, the vertical side is 2. What's the vertical side of my big triangle? Y. So 2 is to y as, in my little pink triangle, the horizontal distance is 12 minus x. And in the larger blue triangle, what's the horizontal length side? 12. Good. So I wrote an equation for that relates x and y, and those are the two variables I'm interested in. So I have a choice here. I could simplify this thing before I start taking DDTs, or I could just take DDT. Should come out the same either way. Do you guys have any immediate preference? No? Okay. So my immediate thought was to cross multiply because that's what you do when you see a proportion, right? But then as soon as I did it in my head, I saw 12 minus x times y, and I thought, oh, then I'm going to have to use the product rule. I think I'll just leave it. So instead of cross multiplying, I am going to simplify each side to make the derivative easier. So instead of 2 over y, I'm going to write 2y to the negative 1. And instead of 12 minus x over 12, I'm going to write 1 minus 1/12 x. So I divided the 12 into both terms in that fraction on the right. So now when I take d dt, it will be a little bit easier. Okay, so the derivative of 2y to the negative 1 will be what? Yep. And then times dy dt. Right. Can't forget the chain rule. All right, and then d dt of 1 minus 1/12 x. Well, the derivative of 1 is 0, so that just goes away. And then the derivative of negative 1/12 x is negative 1/12. But then I also have to multiply by the derivative of the x, dx dt. Okay, so now I plug in my snapshot. Now that I know everything there is to know about this situation and I have an equation with all my variables and rates in it, now I think about my snapshot. So I want to know dy dt is what I'm going to be solving for. So that should be the only thing that I don't plug into. And I know y is supposed to be, oh, they didn't tell me what y is. They told me what x is, right? So I need to be able to plug in here everything except dy dt. And dx dt, they told me was negative 1.6. Okay, how can I figure out y? If I'm solving for dy dt, that can be the only thing left in my equation, my only unknown that's left. So in my snapshot, x is 10. So maybe I'll draw myself another picture here. Can I figure out y if I know that x is 10? How do you know y is 12? Yes, I can use the same proportion that I used to write my original equation, right? 2 over y equals 12 minus x over 2. So I write another proportion, 2 over y, that's the vertical distance of each triangle, equals 10, nope, sorry, 2 over 12. So this is to this as this is to this. And then we just solve for y. Has to be 12. Then we can plug that into our snapshot. So negative 2 over 144 times dy dt to 15ths. So 2 over 144, that would simplify to 1 over 72. So dy dt is going to be 2/15 times the reciprocal of this 2 over 144. So it will be negative 72 over 1. Negative 9.6. And the units on y, the length of my shadow, is meters. And the units on time was seconds. Okay. I drew a picture of a clock, put the hour hand and the minute hand on, and I broke my rule and I drew it at our snapshot in time. But I didn't label theta or x. I labeled them as variables because they're changing, right? As the hands move, the angle between them changes and the distance between their tips changes. Okay, so these are my two variables, x and theta. I definitely have an equation that will relate those two variables if I use the law of cosines. So I've got that part, but what I need is what do I know and what do I want? So the question asked me about the rate of change between the tips of the hands. So that would be dx dt, according to my picture. And I would like to know dx dt at 1 o'clock, which means that theta would be what at 1 o'clock? Pi over 6. Yes, because there's 360 degrees in the circle. Divide by 12, you get 30 degrees. So between any two numbers on the clock, there's 30 degrees, or pi over 6 radians. So I want dx dt when theta is pi over 6, and when x is what? Yeah, I'm going to have to plug into the law of cosines here to find out what x is. So my a and my b are going to be a 4 and a 2. Theta is a pi over 6. Call it x. So I'm just applying the law of cosines to my triangle on the clock. All right, so let's see. 4 squared is 16 plus 2 squared, that's 20. That's 16, the cosine of pi over 6. That's root 3 over 2, right? Okay, so my calculator do the rest. So 8 times the square root of 3, that's the 16 times root 3 over 2, plus 20, square root it, and I get 5.818. All right, so I've got what I want. What do I know? The speed of the two hands, I know the circular speed, right? So let's think about that. How fast or how long does it take the hour hand to go one time around the clock? It takes the minute hand 1 hour to go around the clock. How about the hour hand? 12 hours. Yeah, if it starts at noon, it's not going to point to that 12 again until midnight, right? 12 hours. So my hour hand circles the clock at 2 pi radians every 12 hours. Or pi over 6 radians per hour. Also makes sense, right? Because it's pi over 6 between each number on the clock. So the hour hand moves pi over 6 radians every hour. And then my minute hand like you said, Jacob, it goes around the clock one time every hour. So its speed is 2 pi radians per 1 hour. So the minute hand's much faster than the hour hand. The arc length. So use what, like S equals R theta? Arc length formula. Circumference. 2 pi r. So the problem with looking at arc length is that what I'm interested in is the rate that this distance is changing, not this distance, right? Like the straight line distance, not the curved distance. So if you use arc length to measure speed, yeah, it might come out the same. It might come out the same. I'm curious. I'll have to think about it and we'll see if we get the same answer. Because the speed at which the angle is changing is very closely related to the speed that the arc length is changing, right? Because they are tied together by the S equals R theta formula. Yeah. Okay, so yeah, they might come out the same. All right, so if I know the speed of the hour hand and the speed of the minute hand, what I really want to know is the speed of the angle between the two. How fast is that angle closing, right? Or getting bigger, right? So that the speed that this angle is changing is the difference between these two speeds. So that means I know d theta dt. So let's think about it. A couple minutes before 1 o'clock, my hour hand's over here. I mean, my minute hand's over there, and my hour hand's like here. So if I want to calculate theta, I would do hour hand minus minute hand. I guess it doesn't matter. So pi over 6 minus 2 pi. Negative 10 pi over 6 or 5 pi over 3. Should it be negative? Is d theta dt, is theta getting smaller or bigger as we head towards 1 o'clock? I think it's getting smaller because the minute hand moves faster than the hour hand. So it should be getting smaller, which means d theta dt should be negative. Okay, good. So we did that right. Okay, so that's what I know. I know d theta dt. All right, so now I use the law of cosines as my thing that relates theta and x. So it was 4 squared plus 2 squared plus 2 times 4 times 2 cosine theta equals x squared. Now, let's take that equation that relates x and theta and take d dt of both sides. So I'm going to get negative 16 sine theta times d theta dt equals 2x times dx dt, and plug in the stuff we know. D theta dt I know is negative 5 pi over 3. Theta I know at my snapshot is pi over 6. X at my snapshot I know, I figured it out a little while ago. X at my snapshot was 5.82. And then just solve for dx dt. I'll leave it to you.